Hello everyone, welcome to full revision for practical exam or unit 3 of IAL Edexcel International at AS level. So this paper is all about uncertainties, all about graphs, all about knowing what to do with what equipment, what you're measuring, how to do an experiment, and that's why it's called a practical paper, whereas it's actually a written paper. Anyways, so let's start and dive in. So SI units are basically standard units, and we have a few that you need to learn. So it's 8, but then we actually have 9 SI units. So the quantity of mass has a unit of kilogram, symbol is kg. Length is measured in meters, and the symbol is m. Time is second, and the symbol is s. Temperature is Kelvin, not Celsius. So symbol is K, current is ampere, symbol is A, amount of substance is mole, symbol is mole, and light intensity is candela, which is CD. But we don't actually really need to know about this, so don't worry about this. So remember the prefixes. So if you have a G, that means gigabyte. If you have an M, that means megabyte, kilo, hecto, deca, deci, centi, milli, micro, nano, and pico. We don't really talk about this, but the symbol is P also. And then giga is 10 to the power 9, mega is 10 to the power 6, kilo is 10 to the power 3, hecto is 10 to the power 2, deca is 10 to the power 1, deci is 10 to the power -1, centi is 10 to the power -2, milli is 10 to the power -3, and micro 10 to the power -6, nano 10 to the power -9. So key terms that you really need to know about is range, which is the highest and the lowest value on the instrument that it could measure. Resolution is the smallest division on an instrument. You must know that a meter ruler has a resolution of 1 millimeter, vernier caliper has 0.1 millimeter, micrometer screw gauge has a 0.01 millimeter, and protractor has 1 degrees. So this is a vernier caliper, and it's used to measure lengths up to 100 millimeters or more, so 10 centimeters and more, and the least count is 0.1 millimeter or 0.01 centimeter, and it's used to measure length of small objects, thickness of materials, and the depth of holes. So the depth is actually measured on this side, and how we use it is basically you put something here, and we assure that this screw is tightened, and then we read using this that I'm gonna tell you in a minute. So when reading objects is between the jaws of the caliper, check the reading on the main and the vernier scale when jaws are closed. So this is the main scale. It's the big one that looks like a ruler, and then you have a vernier scale, which is this, which allows for the higher resolution reading. So firstly, you read the centimeter mark of the left of the vernier caliper. So here it's 1, and then find the point where the line matches up. So if you see this doesn't match over this doesn't match over this, only line that matches up is here. So that is on the vernier scale, and this tells you the number of tenths of a millimeter, so that's 0.03 millimeters. And then read the millimeter mark on the left of the vernier scale. So we go 1, 2, 3. So that's 1.3 plus this 0.3, which gives you 13.3 millimeters and 1.33 centimeters. Make sure that you could convert from centimeters to millimeters to meters, from kg to grams, all of that. So micrometer screw gauge looks something like this. It's more precise because it has like a ratchet that turns around and gives you a thimble scale and a main scale that would allow for higher resolution. Anyways, lower resolution, so higher accuracy. So resolution is 0.01 millimeters, and it's used for measuring small bits, thickness, and diameter. So here we have like a very, very small ball. So how you read it is basically you read the main scale first. So each division is half a millimeter. So you read it, and then there are 5 divisions on the main scale to the nearest 0.5 millimeter, which is 2.5 in this case, because we have 5 of them. Let me show you. 1, 2, 3, 4, 5. So that's 0.5 times 5, which is 2.5 millimeters. And then you read on the thimble scale, that each division represents 0.1 millimeter, which is actually the resolution. Anyways, reading the number that aligns with the main scale and multiply this by 0.01, so 17 in this case, because it's 15 and then 2 higher. 17 times this gives you 0.1 millimeters, and then you add to get 2.67. So now we are comparing analog and digital equipment. So analog could read data using a computer and could be analyzed using a computer, and so can digital. Analog is cheaper, digital is more expensive. The accuracy of analog is lower, whereas the accuracy of digital is higher. The resolution of the analog one is lower, so the resolution of the digital one is higher. The sensitivity of analog is way more, which is basically the reason why it's hard to read because of the fluctuations, whereas the digital one displays readings as digits, make it easier to read. And then errors, so this one could have parallax and 0 errors, whereas the digital one can only have 0 errors. So limitations of measurement. So let's first define accuracy. So accuracy is the measured value is close to the actual value. So if I wanted 9.81 and I get 9.80, then my value is pretty accurate because it's really close. And then repeating means that you find different measurements and then find the mean. This also helps using finding anomalies. So if I have all my values are 9.81, 9.82, 9.83, and then one of my values is 6.3, that's definitely an anomaly, so we do not count it in our mean. Precision is how close the repeated values are to each other. So basically 9.81, 9.82, 9.83, these are all close, but if the value that I actually wanted was 10.3, none of them are accurate, but all of them are precise. So when the values are similar, they're precise, and measurements with greater number of decimal places are also more precise. So accuracy is how close measured value is to actual. Precision is how close they are to each other. So if I have an actual value here, and then I have all around these places, they're not close to each other, and they're not close to the actual value, so it's not accurate and not precise. But here, my values are closer to each other, so it is precise, but not accurate, because I need it to be down here. Here, they're pretty close to the actual value, so it is accurate, but it has low precision because they're not close to each other. But here they're close to each other and they are close to the actual value, so high accuracy and high precision. Uncertainty, so basically every value that you measure has an uncertainty, and then uncertainty is measured with two different ways. So one of them is half of the smallest division, and one of them is last decimal place. Absolute uncertainty is the uncertainty as a fixed quantity, so it's smallest over 2 for one measurement, and if you have more than one measurement, like if you have a table, then you get highest minus lowest, which gives you your range over 2. Usually analog is half over small division, and then digital is plus minus the smallest division, okay? Fractional uncertainty. So giving uncertainty as a fraction of the measurement you took. So fractional uncertainty is basically the uncertainty you measured over the measured value. So if I have 0.5 or uncertainty of 10, which is what I measured, that would give me my fractional value. Uncertainty. Addition and subtraction of measurements. So if you add and subtract, numerical uncertainty is added. So if I have 3 uncertainty, so plus minus 3 plus minus 8 is going to give you plus minus 11, and then the value is added or subtracted. So it doesn't matter if you're subtracting or adding, you always add the uncertainties. So percentage uncertainty is uncertainty over value times 100. So when you're multiplying and dividing, the fractional or the percentage uncertainty is added. So if I have 30% uncertainty plus some x with plus minus 20% uncertainty, then my value is going to be either y over x, if this is multiplied, is going to be yx, and if this is divided, it's going to be y over x, and then no matter what, my uncertainty would be 50%, which is a really high uncertainty, so it's not accurate. Note, multiplying or dividing a number does not affect the uncertainty. So if I have 9.81 times like pi, with this uncertainty being like 20%, my uncertainty would be 20% still. The smaller the uncertainty, the more accurate the values. Raising to the power of a to the x, for example. So multiply uncertainty by the power. So if I had like 10 to the power of 3 times x plus minus 20%, you do 20% times 3 to get final uncertainty. Uncertainty for a range of values. So before you actually average it or find the mean, which is the sum of the total over the number of the total, you should cancel out any anomalies. And then the range of values is going to be, the uncertainty of the values is going to be range over 2, which range is maximum minus minimum. Other things to note is that the larger the measurement, the smaller the uncertainty. The percentage uncertainty, because we also already said the percentage uncertainty is uncertainty over value like measured times 100. The bigger this value, the smaller this uncertainty that's going to give us, okay? Percentage difference. So this is basically how much your value is deviating from the actual value, or the experimental value is different to the actual. So how you calculate that is you get the difference between the values, and then you divide by your experimental value times 100. So now definitions that we need to know. Calibration is basically comparing reading of one instrument with another that has a known accuracy. So like an example of this would be making sure that your scale reads 0. And then control variable is what needs to be constant. So if I'm like measuring like the kinetic energy, my temperature in Kelvin actually needs to be constant. And then dependent variable is basically what's being measured, what's being tested. What are you trying to find in this experiment, right? So a fair test is one that independent variable is allowed to affect the dependent variable. So you might ask, what is the independent variable? So it's a variable being altered in an experiment to affect the dependent variable. So I'm changing like my height to understand if like the speed is like the same everywhere. So if I'm changing my height, then that's my independent variable. What I'm measuring is like, I don't know, the time and the distance, and then what I'm controlling throughout this whole thing is like the mass of the object, for example, or the place that I'm doing it, or the height. So random errors are unpredictable variations in measurement, and they're reduced by repeating or calculating mean. Resolution is the smallest reading on an instrument. Systematic errors causes all readings to differ. So systematic errors could be something like 0 error, So like if I go on a scale and the scale already reads 15 and my weight is like 100, then my actual weight is 100 minus 15. So that's a systematic error. It doesn't matter who gets on that scale, everybody's going to have 15 kilograms extra weight. So by a fixed amount. This cannot be corrected by repeating. So it does not matter how many times I get on that scale. If it's not on the 0, the systematic error would happen every time basically. But then it could be only corrected if you change the technique or the apparatus. So you could change the instrument, or you could just change the apparatus or the technique you're using. Make sure to do as many possible past papers. Watch this video twice the speed, as many times as you need. YouTube videos are perfect. Like whatever you don't get, just watch a YouTube video, and do not stop doing past papers, guys. Measure how the marks you would like you to answer, and good luck. I hope everybody does really, really great in that exam.